I'll be speaking about some of my postdoctoral work. This work has appeared in the IEEE ION PLANSx meeting proceedings, and it's currently in submission to the Transactions on Aerospace and Electronic Systems with a preprint available on the archive. Commercial development of low Earth orbit has reached a breakneck pace. This presents us with a remarkable opportunity to augment GPS like never before. Allow me to outline the problem we're trying to solve. The domain is positioning, navigation, and timing. The problem is assurance. Assured PNT, or APNT, has become an urgent national priority. Precise synchronization is required for long-range wireless networks with high spectral reuse. Precise timing also enables observation of phase gradients within the national electrical grid, a critical tool for load and stability monitoring. In the agricultural sector, precise positioning allows farmers to use substantially less pesticide. In the maritime sector, it provides situational awareness for safe maneuvering. In the aviation sector, it provides critical navigation safeguards. In E911 applications, it guides first responders, and in many other sectors of the national and global economies, it leads to improvements in safety and efficiency. So what is it about GPS that is not adequate to meet the needs of the country in terms of assured PNT? Professor Brad Parkinson, the father of GPS, has spent the past few decades fighting the encroachment of civilian sources of radio frequency interference into the neighborhood of GPS. Some are calling this a losing battle. Under the banner of 5G, it seems that loud terrestrial signals will soon elbow their way into the L band. These signals aren't on the same channel as GPS. Why would a scientist and leader of Parkinson's eminence be so concerned? After all, isn't this just a matter of putting better filters in GPS receivers? The problem is that GPS signals are incredibly faint, well below the thermal noise floor. The GPS satellites are 20,000 kilometers away. Each signal divides a few hundred watts of power across half the planet. Near a significant source of interference, GPS signals are simply too faint to detect. In our experience, it doesn't take much. An HDMI cable running too close to a GPS antenna, even if the cable is shielded. A nearby processor core with an unlucky clock harmonic. These things will knock out a GPS receiver operating at the highest level of precision and force it to fall back into a low precision mode. Off-the-shelf jammers and free signal spoofing software up the ante even further, disabling even the low precision mode, or what's worse, deceiving GPS receivers into reporting a malicious signal as valid. So, is Dr. Parkinson justified in going nonlinear against civilian threats to GPS? The fact is, GPS is extremely vulnerable to interference. So are all of the European, Russian, and Chinese global navigation satellite systems. All use satellites in medium Earth orbit or above, and there's no silver bullet-shaped antenna here. Power is limited, Earth is big, paths are long, signals are weak. I think it's fair to say that Parkinson's view of the threat is realistic. What justification is there for the scale of his response? Is he passionate about this just because GPS is his brainchild? No. Those precious GPS watts from medium Earth orbit support an estimated $1 billion per day of critical economic activity in the US alone. Compared to the cost of the program, the return on investment for GPS is in the neighborhood of 20,000%. Every 3 days of those satellites' operation is literally worth their mass in gold. If the United States had crown jewels, GPS would surely be one of them. There are many further threats to the Navstar global positioning system in the world today, both inadvertent and deliberate. Dr. Parkinson's call to action involves 3 responses: protect GPS, toughen it, and augment it. These are 3 lanes on the road to assured positioning, navigation, and timing. PNT from low Earth orbit will provide augmentation. Dr. Tyler Reed, recently from Stanford, now with Sona Space Systems, authored a series of papers in 2016 and 2018 that were our starting point. His proposal was ambitious, but we think it wasn't ambitious enough. What we are calling fused LEO GNSS is a proposal to provide PNT from low Earth orbit without new hardware or spectrum. Todd and I developed this idea over the past year and a half, and we pitched it to the Army Futures Command as part of a broader study into Assured PNT. They loved the idea, and as we have worked out the details, we've become increasingly confident that this will work. We've just begun year 2 of a 3-year funded project with AFC, and at their request, we've adjusted our schedule to focus even more tightly on this idea. But before we hitch our PNT wagon to low Earth orbit, we need to stop for a reality check. Exploitation of low Earth orbit, or LEO, has followed a pronounced hype curve. In the 3 decades between Goddard's first successful launch and Sputnik, rocket technology captured the popular imagination. But even by the time of the first commercial launch, Telstar 1, attention was moving beyond LEO to geosynchronous and geostationary orbits. And this is for several reasons, but fundamentally, when you're providing service to a specific region, geosynchronicity is really valuable. And visibility to a hemisphere is a far more marketable proposition than visibility to a few 100-kilometer circle on the ground. 2 major efforts to commercialize LEO in the 90s led to financial ruin. It seems that commercial progress in LEO comes one bankruptcy at a time. We are optimistic that the current crop of commercial LEO endeavors will succeed, but we have no illusions here. The economics of commercial LEO have never really worked out in the past, and the burden is on these new entrants to show that they will be more than a flash in the pan. But if they do survive, we've got something magnificent on our hands. So these 3 contenders are building massive LEO constellations for global broadband wireless internet. We are talking about tens of thousands of privately funded vehicles that are going to fly whether or not we take advantage of them, and well in excess of $10 billion of investment. Can we exploit these platforms to provide PNT service? The traditional way would be to develop a hardware PNT hosted payload to be carried on each of these commercial vehicles. A hosted payload gains access to costly resources at a steep discount: orbital slots, launches, station keeping, power, telemetry, and precision orbit determination. These costs are already borne by the primary broadband internet mission of these satellites. Of these 3 mega constellations, SpaceX's Starlink is in the pole position with 775 satellites launched. OneWeb has launched 74 and is just coming out of bankruptcy. Kuiper Systems hasn't launched any hardware yet. For concreteness, I will assume a Starlink platform for fused LEO GNSS, but this is not the only option. There are significant costs associated with designing, building, and flying a hosted payload LEO PNT solution. Besides hardware, one must also acquire a wideband allocation of spectrum, which is no easy task. Tyler Reed and his colleagues at Stanford have argued that with a few megahertz of spectrum, a hosted payload could be built to achieve 3-meter positioning. Reed also raised a game-changing question. What if the LEO constellation is not entirely independent, but depends on GPS? So ideally, each satellite in the constellation would carry a precise clock, and there would be ranging sensors for measuring the distances between pairs of nearby satellites using lasers, for instance. This would allow us to solve a massive nonlinear least squares problem to jointly estimate the orbital parameters and clock offsets of the entire constellation. Every so often, the solution would be updated with the latest observations, and it would be uploaded to the satellites to be shared with users on the ground. Users need this orbit and clock ephemeris data to perform multilateration. Cutting-edge clocks for space applications have historically had high failure rates, but proven, miniaturized, older generation designs are available, Such a GPS-independent LEO PNT constellation could work. The sticking point in our minds was the inter-satellite ranging. Starlink's first generation of satellites don't have inter-satellite link capability, and we wanted to eliminate every barrier to deploying PNT from LEO. Without these inter-satellite links, ranging observations would have to be between satellites and ground stations. In this mode, it would be very difficult to fully observe satellites, clocks, and orbits over Antarctica or the Pacific Ocean, for instance. A large number of ground stations would be needed in very remote locations. Reed's alternative, what he calls multi-tier GNSS, calls for each LEO vehicle to carry a GPS receiver. If orbits and clocks are estimated on board, there's no need for inter-satellite ranging or even satellite to ground ranging. This was the point of departure for my work. Todd and I wished to understand the trade-off between more frequent ephemeris updates on the one hand and less expensive clock hardware on the other. But we were still tied down by the way of thinking that comes from traditional GNSS. That traditional wisdom involved several assumptions that we soon realized can be bypassed. First, that ranging errors at the user are dominated by the limited bandwidth and strength of the signal, what we call receiver noise effects. Second, that the user must coherently integrate ranging signals for roughly 1 to 10 milliseconds to compensate for low SNR. Third, that data modulation on the ranging carrier must be slower than the coherent integration time, so that receivers don't have to guess which phase the carrier has at any given time. And for this reason, ephemeris takes several seconds to download. Because ephemeris takes seconds to download, it must encode a model valid over at least a similar interval. But none of these constraints apply to the broadband internet service itself on board these LEO vehicles. Where traditional GPS signals have a bandwidth of a few megahertz, broadband LEO internet service has been allocated several gigahertz in the KU band. Individual channels are 50 megahertz, and a typical signal-to-noise ratio over that bandwidth is 6.4 dB. Compare this with GPS, where the signal-to-noise ratio over a 2 megahertz channel is negative 27 dB on a good day. Even without spreading gains, LEO signals are much, much more powerful. Suppose we could do PNT over one of these broadband internet channels. With a 50 megahertz channel and a positive signal-to-noise ratio, the contribution of receiver noise to the overall error budget becomes negligible. In a sense, this gives us more than we bargained for. Amdahl's law suggests that for a system with many components, it's wasteful to over-engineer any one of them to the point where its cost becomes negligible. To put that another way, it would be preferable to spend some of this excess ranging capability, which is deep into diminishing returns, to gain other advantages. And the first advantage that we buy with this currency is insensitivity to modulation. In traditional PNT systems, the basic signal waveform would be a pseudo-random range encode, possibly with some Manchester encoding or a more elaborate binary offset carrier scheme. But if we're in the business of taking full advantage of the broadband LEO satellite hardware, then it would be greatly preferable to not introduce a custom waveform. Introducing a custom ranging waveform might require revisions to the modem silicon on the satellite, which we view as a non-starter. So, what is the waveform that these satellite modems do produce? We argue in our paper that there's every reason to believe it will be a variant of OFDM. The problems that these waveforms need to solve are just too similar to the problems faced by LTE signaling to expect satellite providers to reinvent the wheel on modulation. OneWeb has been open about their use of OFDM, while SpaceX has not made a public statement to my knowledge. Can we use OFDM for ranging? Yes, it is suboptimal, but only by a constant factor. Under additive white Gaussian noise, we can place a lower bound on the uncertainty of the user's ranging measurements. In the time domain, this bound varies inversely with the root mean square time derivative of the signal waveform. If the signal varies slowly, the ranging uncertainty is large. If we look at only those signals which are real, band limited, and power limited, this bound is saturated by beating sinusoid. So if you have a band that runs from 1 gigahertz to 1.1 gigahertz, then the ideal signal is going to look something like a carrier at 1 gigahertz and another carrier at 1.1 gigahertz. And the net effect is going to be something like a beating sinusoid when you look at the real voltage. As I say, OFDM does not saturate this bound, but the gap is not very large. OFDM is suboptimal for ranging by a constant factor of √3. These broadband internet radios, channels, and antennas are therefore more than adequate for PNT. The contribution of receiver noise to the final positioning error in my estimates is only 5 millimeters RMS. This is a subdominant contribution. So even though we're using suboptimal signals, we don't lose anything substantial. So let's step back and revisit a fundamental question. The question is, what is absolutely necessary for a satellite radio navigation payload? There are really only 4 elements. What is a PNT payload once you separate out the features that are provided by the hosting satellite? If you could take for granted station keeping and precision orbit determination and telemetry and power and so forth, what would you still need? Clock, transmitter, spectrum, antenna. Commercial internet satellite already has a clock. It's not up to atomic standards. It already has a transmitter. The waveform is adequate. It already has a spectrum allocation. And these satellites have highly directional, electronically steerable antennas. So this is what fused LEO GNSS is. We shoehorn the needs of PNT into the limitations of existing commercial internet satellites. We fuse the PNT functionality into the existing hardware. At first, there wasn't enough public information available to evaluate this idea thoroughly. There were too many unknowns, but Willie Nelson at Army Futures Command has made opportunities for us to speak with one of the major constellation providers. It now appears that the answer is yes across the board. Yes, the existing communications hardware, with perhaps some modest upgrades to the onboard GPS receiver, can do everything we need to provide better than GPS user positioning error on the ground. This assumes, of course, that a GPS signal is available in orbit, but it is much more difficult to jam the signal there than it is to do so on the ground. So we now have solid ground for optimism that a commercial multi-tier fused LEO GNSS will work, and will work better than many solutions available today. We believe fused LEO PNT is going to be one of the key answers to assured PNT. Next, I'm going to take you through some quantitative assessments of what this proposal gives. Then we're going to go back and talk about the concept of operations and the costs associated with providing this service. In our earlier publication in IEEE ION plans, we set out to quantify the gains that were possible using a fused LEO GNSS solution compared with traditional GNSS. And when I say traditional GNSS, strictly speaking, I'm not comparing against the L1C, the L5, the new and upcoming signals that we are all eagerly anticipating, some of which are already in the air. I'm just comparing against traditional GNSS. Compared with traditional GNSS, the signal power available at ground level is 1,000 times greater. The limitation here is determined by the ITU radio regulations on non-geostationary K-band services. Because this spectrum is reused from services that were already in place from geostationary orbit and terrestrially, there are exclusion bands where you can't point signals too close to geostationary orbit from the ground, and you can't point signals from the satellite down to the ground along a line parallel with the line of sight to geostationary orbit, and so on. But the flux limitation is the crucial one. Compared with the types of antennas that you can build in a few tens of centimeters of volume, the sort of off-the-shelf, state-of-the-art antenna for outdoor GNSS operation would be the choke ring. Compared with an L-band choke ring of similar dimensions, a K-band phased array can much more effectively reject jamming signals coming from the horizon. Positioning with the fused LEO GNSS solution is extremely rapid. Depending on how much service the users of this system want to pay for, you could get a fix within as little as 20 milliseconds. The time here is currently dominated by the time needed to reconfigure and steer the receiver's phased array on the ground. There's no point in having satellites send down signals so quickly that the user can't keep up with them. The large number of satellites makes fused LEO GNSS an unappealing target for anti-satellite warfare. There is a nightmare scenario where in a shooting war, we lose GPS. That would be a generational tragedy in terms of the value that it brings to society. If PNT were coming from a constellation with 1,000 times more satellites, it would start to be far too costly to contemplate shooting those satellites down. Now, as long as the system is ultimately reliant on GPS to provide the gold standard signal from above, it's still vulnerable. But that is an avenue of future work. As these satellites gain intersatellite link capability, we expect that it will be possible to eventually remove the dependence on GPS. But we are outlining a system that for the time being does not require atomic clocks. And that makes a big difference in terms of whether the hardware that's already in orbit can participate in providing these new signals. Compared with traditional GNSS, with the L1 CA signal, these ranging bursts will have 25 times more bandwidth. They'll also be extremely short. We're looking at half a millisecond long bursts. This is actually overkill. Our understanding is that the burst duration will be reduced to whatever the granularity limit is of the satellite's onboard scheduling hardware. A single half millisecond ranging burst can easily accommodate up to the instant orbit and clock ephemeris from the transmitting satellite. And because this ephemeris data is up to the instant, there's very little need for a holdover in the satellite clocks. Our estimates indicate that oven-controlled crystal oscillators are adequate. Using real-time ephemeris, the 95% positioning error over the US for single epoch pseudo-range only positioning could be as low as 41 centimeters. It bears repeating that zero lag ephemerides would never have been possible with a traditional GNSS signal structure. In such signals, the data bandwidth is on the order of 50 bits per second. If you look at the wide area augmentation system, it could be as high as 1,000 bits per second. But this is on another level. Data bandwidth, which seems like it would be extraneous for PNT, is what allows fused LEO PNT to broadcast up-to-date clock estimates. And these up-to-date estimates are what allow us to eliminate the need for atomic clocks. If fused LEO GNSS is not free to use, we must consider the question of who will pay for it. That is, the market for radio navigation. How could fused LEO GNSS be better than free? Well, to be competitive, it will have to offer such significant performance or flexibility advantages over traditional free-to-use GNSS that it's worthwhile to buyers. It must also be sufficiently inexpensive to supply, both in upfront costs and in consumption of satellite resources, so that service providers can afford to set a low price point, despite diverting satellite resources away from potentially lucrative broadband internet service. We spent a great deal of attention in our more recent paper, the one that's in submission, studying the resource utilization associated with PNT service. For each spot beam operating over maybe a 20 kilometer to 40 kilometer circle on the ground, the amount of resource utilization that we anticipate is needed is on the order of one of the users in that city pulling down a 1 megabyte per second cat video. And you know, it's possible that this will be the straw that breaks the camel's back, but one of the things that's really remarkable about the fused LEO GNSS concept is that one stream with this resource utilization serves all the users within a geographical area, within a single cell of operation. This is not like the broadband internet service. The broadband internet service suffers from a linear scaling of resource utilization with number of customers served. So there's a certain population density where the amount of bandwidth that would be available to each customer just becomes uninteresting to consumers. So our understanding, and I believe based on public statements, SpaceX's understanding as well, is that for the time being, this service will mainly be competitive in rural areas. But fused LEO GNSS doesn't have this problem. If the number of people paying for PNT just depends on the population density, then in fact, this would be a perfect way for operators to monetize their capabilities when their satellites are over urban areas. A price point comparison for a PNT customer willing to pay a subscription fee might be the incorporation of an ongoing RTK differential network service fee into the lump sum cost of the General Motors Super Cruise feature. This is, even though the market for PNT has traditionally had a cost of free, this is sort of our first inkling that there's an appetite for non-free PNT service. It's just not visible to consumers at the present time that they're paying a subscription fee. If the service is competitive for civil use, it will be more than competitive for relatively cost-insensitive military users. The bottom line is that fused LEO GNSS offers superior and configurable jamming resistance, superior positioning accuracy, and low cost. We don't think that the government will balk too much at turning to a commercial service provider. And it will be up to individual customers whether they're interested in buying PNT from a private company. We would love to see a future evolution of this concept that eliminates its dependence on GPS globally once inter-satellite links are available. We also expect that it will be possible to reduce the rather large form factor of user antennas by giving up some anti-jam advantage. Our current plans focus on static and vehicular applications to negate the concern of the large form factor. I'd like to get in a little bit to our thinking about costs. And more than that, our thinking about what is really required from a broadband LEO provider to support a PNT, a fused LEO GNSS mission. Each of these constellation providers has built their satellites with highly directional antennas pointed at the ground. And they're all subject to this ITU limitation on the number of watts per square meter, number of Janskis that they supply to users, so as not to disrupt K-band terrestrial comms. The consequence of this is they have to be careful to spread out the power they have available. They can't just point one beam of one satellite at each customer. They have to make sure that each area is served by a single beam at a time. So this is cellular service. In effect, the world is divided up into cells. At any given time, each cell is served by one primary satellite. Now for GNSS, it's not enough to get one signal coming down from the sky. In order for a user to perform multilateration, we need multi-signals. So we introduced this concept of secondary assignments of satellites to cells. In addition to this primary assignment, where one satellite is going to provide cat videos to a particular cell at a particular time, there will be a number of secondary assignments, which are other satellites that have been tasked with once in a while, once per second is our sort of typical parameterization. They will pause whatever they're doing on their downlink, reorient their electronically steerable antenna to point it at this cross-cell location and provide a burst of ranging signal. And then they'll switch back to the cell that they're primary for, and they'll resume providing internet service. These cross-cell ranging events have to be scheduled centrally, because unlike most of the other operations of the internet constellation, these decisions are non-local. If you schedule a ranging burst from satellite 1 to cell 5 at a certain time, then the primary satellite for that cell needs to know to stop downlinking for a brief window in order to not collide with the ranging signal that's coming in from another direction. Now, this is not an electrical limitation. As we say, these even the receivers have highly directional steerable antennas. The issue is regulatory. If these two signals arrive in the service area at the same time, the flux limit would be exceeded. So we started drawing diagrams to help us articulate what exactly are the constraints that this global scheduler would need to enforce. And the idea is that this global scheduler is some sort of enormous, greedy SAT solver, or perhaps it can be approximated with min-cost flow. But in any event, we wanted to understand how constrained that scheduling problem is. Once you add up all the signals that are needed from all the satellites to all the service cells, how much freedom does the scheduler still have as a proxy for how quickly will the scheduler be able to find a satisfying schedule? So what I've depicted here on the left is a cartoon of one service cell that's being served by two satellites. And transmitter 1 is the primary for this cell, and transmitter 2 is one of the secondary assignments for this cell. And the signals are going to come in at different zenith angles, theta 1 and theta 2. And we use capital D to represent the diameter of the service region, or the size of a spot beam, roughly. And the west to east direction is arbitrary. It's just there to provide a reference. And on the right-hand side, what we show is sort of a space-time diagram of how these signals propagate. So in the right diagram, you can see where TX1 is on the, it's near the ZX plane. That transmission expands outwards in a cone, and it continues for a time T burst. The cone of signal, or rather the space between the start cone and the end cone, sweeps out a volume which sooner or later reaches the ground. The ground is this Z equals 0 plane. And the shaded parallelogram, approximately, is the time that a signal is arriving as seen from the perspective of a user standing at various places in the cell. At the top right, the user is further to the east. At the bottom left, the user is further to the west. And because the satellite is off center to the cell, the signal sweeps across the cell from west to east. Transmitter 2, in a different place, produces a cone that sweeps from east to west. And so we have to account for all of the time that the channel is idle when we answer the question, how costly is it for the provider to set aside some time, some resources to provide this PNT signal? Anytime that they can't provide internet service is cost that accrues to the PNT mission. So we take this diagram as our template for understanding what times we need to calculate, how we need to add them up. Now, the schedule that is computed centrally and shared with the satellites is cyclical. There's some time, T period, over which the schedule repeats. And because the satellites are in a bunch of different orbital elevations, there's no guarantee that the periods of their orbits are not relatively prime or incommensurate in some irrational way. As a consequence, we can't say that one period is going to work, or one schedule is going to work forever, or even that a schedule can be reused 10 minutes or an hour from now. These schedules, as far as we can understand, would need to be recomputed periodically. But again, we're just trying to get a handle on this question of how close is this satisfiability problem to the threshold of hardness? And what I'm showing on the left is a cartoon of 1 second of time at one receiver. From the receiver's perspective, bad things happen if 2 packets are arriving at the same time. And again, this is a regulatory limitation, not an electronic limitation. So we call the schedule infeasible if 2 bursts arrive from 2 satellites at the same time. We call a signal feasible from the perspective of this user if the signals from 2 different satellites arrive with enough space between them so that the receiver can safely reconfigure its phased array and be ready to receive a signal coming in from a different direction. And the same, we consider schedule feasible when there's no gap between 2 bursts if they come from the same direction. On the right, I've unwrapped this clock. So the axis that runs around the perimeter of the clock now runs from left to right, the time axis. And so this is toroidal in that way. And here I've blown up the durations of the bursts by a factor of about 70 for the purpose of visualization. Actually, this cube is almost completely empty in practice. This cube represents the channels that are reserved in certain cells at certain times. If you were to try to send an additional signal to a certain cell on a certain channel, And this cube says, no, no, that cell is red. It's in adjacent cell exclusion mode right now. That's the state it's in. Then what would happen is the overlap of the two beams, the satellite beams coming down to the ground, would be such that there would be significant interference to the user receiving the blue burst adjacent to the red rectangle, or the green burst adjacent to the red rectangle. That is, if there are two neighboring cells and beams come down from the same or different satellites on the same channel to these two adjacent cells, they may not be decodable by users who are too close to the boundary between those cells. So we exclude that, and we call it adjacent cell exclusion. And we also introduce switching times. These are the black rectangles. No two blue rectangles can be closer together than the switching time, or else the user in that cell can't switch their antenna fast enough to pick up both signals. And the green corresponds to signals that are coming down from the satellite that is primary for this cell. So this is sort of the characterization that we use. And in our archive preprint and in our submission to the transactions on Aerospace Electronic Systems, we quantify all of this. What you're seeing here is a little Python script that generates a schedule, sort of a miniature simulation. And what makes it not a faithful simulation is that I've decoupled what happens at the transmitter from what happens at the receiver. So this is sort of a cartoon of what happens if you ignore the constraints at the transmitter and consider only the constraints at the receiver. So what are the constraints at the transmitter? We have a very complementary situation. Again, a schedule is infeasible if it calls for a single beam of a single satellite to transmit two different signals at the same time. A schedule is feasible only if two different outgoing signals pointed in different directions are separated by an adequate time for the transmitter phased array to be reconfigured. And the schedule is also feasible if two bursts are back to back, but they're directed in the same direction. On the right, we're showing a slightly different visualization from the previous. Now that we're at the transmitter end, we have to be a little careful. Not all channels of all beams are truly independent. If you command a certain beam to steer and point in a different direction, that doesn't only disrupt one channel, it disrupts all the channels on that beam. And we've done our best to estimate how many that is. It may be somewhere between 8 and 15 channels per beam. So we show adjacent channel exclusions. And an adjacent channel exclusion encodes the status that a given beam on a given channel is unavailable to provide primary data service because it is busy allowing some other channel on the same beam to provide cross-cell ranging. Other than that, this is a very similar situation. We have switching time reservations, we have cross-cell ranging and primary cell ranging reservations. And this, so we would call this the TX cube. This TX cube encodes at what times in the white areas would a given beam of a given satellite be permitted to transmit cat videos. At times that are colored in, that beam would be spoken for. And again, I've amplified the lengths of these bursts for visualization purposes. In reality, the lengths of these boxes would be about 1/2000th of the width of this cube. So this problem that I've been articulating sort of visually, we would call this the central GNSS scheduler. It's not responsible for scheduling internet traffic. What it is responsible for is working out the assignment of which satellites are providing primary and which secondary ranging signals to each cell on the surface of the Earth. And the number of secondary assignments to each cell needs to be, let's say, 4, so that primary plus secondary works out to 5. 4 is the magic number. With 4 signals, you can perform multilateration and solve for X, Y, Z, and time. 5 gives you better performance and margin for error. If there are blockages in the sky, the KU band is sensitive to moisture in the atmosphere. Or if there are buildings in the way and you can pick up 4 out of the 5 signals, you're still okay. The central scheduler is going to explicitly determine when secondary ranging bursts will go out. These are the ones that cross from one satellite into a cell that another satellite is primary for. And the reason that those have to be decided centrally is because the other satellite needs to be informed in advance that it's going to have to avoid using its downlink during that time. Now, I mentioned that it's only avoiding using its downlink. Why do I say that? It's because in all of our explorations, we have not found any concrete reason why the uplink needs to be disturbed. The uplink can proceed as it did before. We're not encumbering it. There's a small amount of metadata that we need to send up to the satellites. For instance, the contents of the schedule once it's computed. And this works out to a few megabytes of data for the entire constellation of 10,000 or more satellites. So the degree to which we're encumbering the uplink is negligible. The degree to which the downlink is encumbered, we estimate, if you count up all of the constraints at ground level, that Rx cube is about 0.03% full. You could keep adding more and more and more reservations to that cube and until it was full, and you would have filled 99.97% of it with cat videos. The transmit side is a bit more constrained at 0.75%. But we are particularly pleased with these numbers for the following reason. If the satellites are interpreted as internet routers, and if we just think in terms of queuing delays, Musk has made much of the fact that his satellites will have latencies in the 20 to 40 millisecond range or less. He wants this to be suitable for real-time gaming. And he has a lot of stake in that because the FCC has set aside, I think, a $16 billion pot for rural access to broadband. And Ajit Pai, the commissioner of the FCC, was convinced that SpaceX could not possibly achieve less than 100 milliseconds of latency. And Musk was eager to prove him wrong. And it seems that he has succeeded in doing that. So SpaceX has a great incentive to keep their latency down in order to gain access to that $16 billion pot. That is to take credit for providing broadband to rural customers who are underserved by existing telecommunications infrastructure. So why do I bring that up? Well, in a packet switched network with bounded latency, there are often stochastic lost opportunities for transmission. It is difficult to keep a link 100% utilized unless you engage in a little bit of buffer bloat. And if everything is tuned perfectly, and if the gateways were providing an isochronous stream of constant sized packets up to the satellites on a fixed schedule, it would 100% be possible to 100% utilize the downlink. However, that doesn't seem like a likely possibility. Customers of Starlink in particular are going to be rural individuals using standard internet applications and services. And as we all know, internet traffic is bursty. The arrival times of packets at the gateways to be provided to the satellites and then in turn to be provided to the users are unpredictable. And as a consequence, the combination of unpredictable arrival times and bounded latency strongly suggests that less than 100% utilization of the downlinks will be commonplace, even at 100% offered load. So, just like that old story of the professor who filled a jar with rocks and then filled the space between the rocks with sand and then filled the space between the sand with water, we think it's quite possible that the downlink reservation associated with fused LEO GNSS service would fall between the cracks of what simply could not be consistently utilized in the internet service of these satellites anyway. So it may be that this doesn't cost 0.75% of SpaceX's budget, but rather this costs them effectively nothing. That's what we're hoping. It certainly makes it easier for us to make our case, provided that other costs like non-recurring engineering don't dominate. And that's a discussion for another day. So in our submission to transactions on aerospace and electronic systems, we set out to quantify the opportunity costs for various constellation resources in order to provide continuous global service between plus and minus 60 degrees latitude. This is most of the humans on Earth, not quite all, but it is a ballpark figure in our view. If you know where your users are, you don't have to light up the desert with signals. And the reservations and costs associated with quiescent satellites waking up and handling bursts that need to be transmitted to empty sand can be eliminated. So these are upper bounds. The most utilized resource is the serial capacity of the phased array network to be reconfigured. We estimate that that resource is about 5% utilized. Now, we did some more math and we said, okay, suppose that I take away from you 5% of your ability to keep your satellite's antenna pointed directly at your users. That is a little bit of the time I need that phased array to point somewhere else, which means a little bit of the time I need to be filling the registers in the chip with coefficients to be used for phasing the array in a different direction, which further means less of the time I can be filling those registers with updated pointing information that will provide a tighter focused beam on the customer. How much does that hurt? And well, there's still a lot we don't know. We don't know what the budget is for the so-called pointing loss. When you design a system like this, you say, okay, well, suppose that half a decibel is the worst that we're willing to tolerate before we slew our beam to point more precisely at the user. So you design the system so that the number of times the beam can be reconfigured per second is more than enough to keep the pointing loss below a threshold that you choose, say 0.5 dB. Well, a 5% reduction in the rate at which you can steer your beams works out to a 15% increase in the pointing loss in logarithmic terms. So it would go from 0.5 dB to 0.6 dB. And that would be a constellation-wide loss in the link budget, which is concerning. We're eager to revisit that calculation with a little bit more finesse and see if we can iron out the cost that we've articulated there. But it isn't like 5% of the time you can't provide service to your customers. It's more like all of the time your service is slightly degraded. We also combine together the estimates of how full the TX and RX cubes are. We call that the downlink capacity reservation. That's about 0.75%. We worked out roughly how much of the solar energy coming into these satellites would need to be used for providing PNT service. That was also negligible. And as I said before, the uplink capacity reservation was negligible. So I'm going to stop here. I will switch to this slide to prompt any questions you might have, and I would be happy to speak further. Thank you.